much for the invitation to be here. My name is Ian Lamswood. I'm the Global Director of Marketing for Leica Microsystems from the Nanotechnology Division. So you may know Leica from the microscopy side. We are also specialists in sample preparation for electron microscopy. My background and career spans 33 years with the company. My previous life was as a biologist, working in histology and electron microscopy. So this was a very nice start point, being a customer to draw yourself into the commercial world of sample preparation, where I've worked, as I say, for many years, in product development and product management. So these are my fortes. I've done a lot of sectioning, ultramicrotomy, cryo ultramicrotomy, and over the years we've developed into a materials science theme as well. And the amalgamation and combination of materials science techniques and biological techniques has been a real thrust for our business, and it's really been very, very helpful. So today's presentation, I'd like to take you through the latest things and happenings that we've been working on in cryo techniques. Over the past year, we've been developing our portfolio to really push into the world of cryo sample preparation. Because as we've heard, we've seen some beautiful electron microscopes from FEI, and these are marvelous machines, but if you can't get a good sample into it, you can't get a good result out. Rubbish in, rubbish out, the usual story. So we are really here to help push very, very nice samples into the instrument and maintain it. And of course, one of the problems that we have is this wonderful stuff called ice. It exists in many shapes and forms. Vitreous ice is the stuff that we love. Hexagonal ice is terrible stuff. Don't like it. Contamination at its worst. But of course, cryo techniques are the way forward, because the artifact formation during chemical fixation is appalling. You change the structural morphology of your sample. Cryo techniques, cryofixation, freezes the sample in a very rapid process and allows very, very high morphological structural values to be kept and maintained within cells. And this is the key for the whole processes. So with that in mind, we've been developing systems to push this no ice challenge. So the no ice challenge is to, of course, have samples where you can see the structural integrity of the samples, synapse here, for example, without ice. The lower pictures show terrible ice crystal damage, and we want to avoid this. But one of the issues is you can freeze a sample well, but then you have to maintain that as well through a workflow process to feed the electron microscope, and this is also a critical process. So what I'd like to focus on today is where we've been actually developing this type of process. We have 5 different little workflows which I'd like to focus on, and each one has its own little pathway. Some of them around protein crystallography and others in different areas. I thought I'd give you an overview of the whole experience. So I'll start off with some cryo-clem techniques, and then some information about an update on high-pressure freezing, and then a move into the wonderful world of freeze-fracture and transfer techniques to make sure that your sample stays in good condition through a process, and then down to something called ion beam milling, which you may say, well, that's material science, but let's see. So at the end of the presentation, I'll also give you some information on the latest updates and where we are heading for protein crystallography. Meanwhile, back to CLEM, correlative light and electron microscopy. Everybody does this in a different way, shape, or form, combining light microscopy techniques, electron microscopy techniques. And we've moved into the world of cryo-clem, simply to allow you to be able to image those single particles or cryosections on a grid in the light microscope prior to going to the electron microscope. Why? Mainly to save time. If you can analyze and identify regions of interest on your grid in the light microscope and take those positions to the electron microscope, you can save a lot of time hunting around for your specific regions of interest. And that's all we do. We use fluorescence technology, fluorescence microscope, to identify regions of interest. So normally, you would have to check all the way across this grid, and it's a bit like looking for, I don't know, $1 on a football pitch at our level of magnification that we go for. If you can identify your regions of interest very quickly, it makes life much quicker. And of course, this increases the throughput on an electron microscope and saves a lot of time. You don't want to spend hours just searching across a screen. So we developed the CryoClem system, and this is basically a cold stage on a light microscope with a docking station attached so you can move the sample. And there is a cryo objective here as well, and this stage is liquid nitrogen cooled. The sample is plunge frozen, as described previously, or high pressure frozen and cryosectioned, so cryosections on a grid, can be transferred into this transfer system, where they are locked into a little holder, a cartridge, and then we can take the whole thing into the cryo stage of the light microscope. And here, the cryo objective is inserted, and you can image your cryo sample in the light microscope. And here you can observe and define the regions of interest and just find those correlative points. One of the main features of this is the objective. This was developed by Leica, and it's got a ceramic nose so that it can withstand the around 200 degrees centigrade change in temperature from the cryo chamber through to the room temperature. And further up, there is also an insulating layer to stop this cold spreading through the rest of the microscope to give us some stability. So we developed this workflow to allow us to take a sample from freezing through to the light microscope for very quick analysis to find the regions of interest. And then from here, we can take the grid through to a transfer system where we can, with these two little holes here, we can dock our little cryotransfer system here, and into the other one, we can dock a cryo TEM holder. So you can do a transfer inside here under nitrogen conditions, low temperature, and without any ice contamination, and then off to the cryo TEM. So this is one of the important workflows which we've been working on, and it often starts off with high pressure freezing. High pressure freezing is a very, very useful technique. If you're not working on single particles and plunge freezing, this is the preferred technique for preparing samples. What we do is we take a sample and we put it under 2,000 atmospheres pressure and then freeze. And by doing this, we can produce a vitreous sample. And this technology is now used not only on its own, but we've started to utilize high-pressure freezing to involve other techniques as well. And the other techniques involve light stimulation. So light stimulation has been used for triggering activities in cells, and especially synapses and neurotransmitters. And here we can activate cells, stimulate them to produce vesicles, release the acetylcholine into the synapses. And of course, if you know when you're triggering this, you can then stimulate a sequence of events to show exactly what you want to see through a cycle of a vesicle, for example, in this case. And this has been done and shown in Nature. This is Erik Jorgensen's work showing the stimulation of vesicles. But the technique is very, very simple. We insert a light module of a specific wavelength. You can choose the wavelength, and you simply activate the system to give a stimulus of light at a point before freezing, which you can choose. The sample itself is located in a small ring here. So this is the sample carrier. The carrier goes in here. It can be on a sapphire disc if it's maybe a cell culture. And by closing this red cover, it activates the cycle, and it's as simple as that. So high pressure freezing made simple. Close the lid, and it fires away. And your samples drop into these liquid nitrogen cooled containers. The sample itself can then be used for a variety of follow-on techniques, from simple processing, sectioning into the electron microscope, or in this case, this is sunscreen lotion that was frozen in the high-pressure freezer and then freeze-fractured. This was UV stimulated, so UV light, of course, is going to have an effect on sunblock to stop pale people like me from going red. And this can then be seen as changes in the electron microscope. So we can use these pathways to help us. And this cryopreparation freeze-fracture pathway is very useful for getting a different view on the world. Instead of looking at a slice of a sample, you can freeze cells and break them open, and the fracture follows the line of least resistance, which is through the membranes. And we have an instrument called the ACE 900, which is a new freeze-fracture device, which has been built specifically for this. So we can freeze our sample and then take it under special conditions into the freeze-fracture device, where with the help of E-beams, E-beams here, we can coat the sample. So we can break it open, and inside the chamber there is a knife, so we can split open the sample, which would be sitting on this surface here, and break it open and then coat the sample. Once coated, we get an image something like this, showing the membranes running through the cell. This is a euglena sample from one of our first beta tests. This instrument is brand new, so we just did some tests recently to show this technique. And this sample is frozen, and it's kept frozen and imaged frozen in the Cryo SEM. This sample has been freeze-etched, so in the SEM you can remove some water to reveal more detail. And we can use our frozen sample in two ways. We can make a replica from the frozen sample, remove the sample itself and just leave the carbon and metal coating and transfer that to the TEM. Or, as mentioned, we can take the frozen hydrated sample itself and transfer it to the Cryo SEM. So the Cryo SEM route involves a little system here called cryotransfer, and as you can see, this locks onto the freeze-fracture device and onto this transfer station. This enables us to take a high-pressure frozen sample into the cryotransfer station and then to any sample preparation system that we like, that has been equipped with a dock to take this. So this is a vacuum cryo transfer system. So it's cooled by liquid nitrogen and under vacuum. And this allows us to take us through to Cryo SEM techniques, for example. These ports on the side allow us to move to the Cryo TEM as well. So here is our dock, which fits onto a Cryo SEM and onto our coaters. So we can come from a Cryo SEM or FIB, for example. If you've been doing some FIB techniques, you may have a lamella to carry over. You can take your lamella from here into the chamber and link onto here through to the Cryo TEM holder and off to the Cryo TEM. So you have a link through where you can have a contamination-free movement of sample. So we can link to many different techniques, from pre-preparation from a glove box. We can link this into a glove box system, right the way through from freeze fracture or coating through to the Cryo SEM. So these are the workflows that we've mentioned. So what about this interesting step called cryo ion milling? As a biological technique, it's not really used, because its main use is for industrial sample preparation. So what is it? It's basically a machine with argon guns inside, and you use these argon beams to smooth and flatten a sample. So it's polishing a sample using argon beams. We put a mask in the way of the sample area. This mask protects the rest of the sample from the argon ions, and we use a collision cascade effect to knock out the sample just using the argon ions. And we prepare a very flat and large surface. So it's called broad ion beam milling compared to focused ion beam milling, because here we can produce a 1/4 micron area of sample. 1/4 millimeter area of sample. So very, very big in comparison to fib. Normally used for microelectronics, this is a cross-section of a chip, and this is a gold wire bond inside a chip, and this is a failure analysis technique, so we can see the failure here was the gold wire bonding itself. So this is why the mobile phone failed, or whatever the chip was used for. We can also use this technique for preparing other samples from silicon carbide. This is sandpaper. This is a veneer, and this is a cross-section of an ultra-thin section on a grid. So that's an ultra-thin section, 50 nanometers, on an EM grid, so we can slice very simply through it. However, what about cryo? What about our sensitive samples? We had a customer who wanted to prepare a sensitive sample, so we decided to do a quick test first. And the poor unfortunate test sample was a gummy bear. I don't know whether you're aware of these little chewy sweets, but it's a little guy that had his head decapitated, unfortunately, and placed into our ion beam miller. And subsequent effect was we fried his brain. So we developed from this a cryo stage. We held him at 150 degrees centigrade and successfully cut through the head and produced this very large area of flat surface. So this was the first step for us to identify that, yes, we can use this process, because a customer had asked us to prepare a sample of a water-soluble polymer. And same thing again, room temperature, it failed. Using cryo, we managed to maintain a beautiful structure. So you could say, well, why not just use a cryo ultramicrotome and slice through it? Because it was water-soluble, when we took the sections out of the chamber of the cryo ultramicrotome, it attracted moisture, and so the water-soluble component started to dissolve. With the ion beam miller, we can hold it inside a chamber until it warms up and keep it away from moisture. So we managed to maintain this structure and prepare these water-soluble fibers. So this gave us the idea of, well, if we've got a system where we can prepare a sensitive sample under cryo conditions, if we can link to it, then we can maybe think about biological samples. A customer came to us with a problem. They'd been trying to section and face a coral polyp. And coral, as you know, contains calcium. And as we tried to section it, it just pulled the samples to pieces because of these spicules of calcium running through the cells. So we thought of this technique. Maybe if we could freeze a sample and get it in there, we'd have a chance of doing something. So we developed a cryo saw once we've frozen the sample is frozen between two metal planchettes. So we'd need to cut through the metal and the sample to remove most of it so we can get at the sample itself. So we developed a cryo saw which helped us to cut through the sample and through the planchette to hold it with a little mask here, and therefore allowing us to have a sample just sitting above a mask as shown in the previous diagram, so we can just bombard it with argon ions to flatten the surface. So we did this, and we managed to get the sample into the tick. We mated up our two systems and got the cryo workflow started. And we developed this workflow showing high pressure freezing. We froze our sample through to the cryo saw, to the ion beam miller, and then to the coater, so we can dock here and here, and then off to the cryo SEM. So this was a new workflow for us. which we found subsequently useful for everything from lithium batteries through to biological samples. And for example, lithium batteries, we don't need the cryo side, just the vacuum to hold it, preventing any oxygen getting at the sample. As you can see the difference here, this is a well-preserved sample, and this is one subject to oxygen. So lithium is highly reactive, of course. What about our biological samples? There was an unfortunate asparagus plant sitting in my colleague's office, so we utilized the leaf of the asparagus plant for our first experiment. And as you can see, we ion beam milled after freezing the whole of a cross-section of a leaf. So this was a good step into the direction we wanted to go. To give you an idea, if you focus ion beamed this sample, you would get an area this size. So this led to the thought of maybe broad ion beam milling would be a good step in the processing for FIB techniques. If you want to look at a huge area, why not mill it flat first so you can identify regions of interest and do a correlative type preparation. So you can find the regions of interest before you go to the FIB. This was the first real experiment that went through in Harvard, and this is a cross-section of a pine needle leaf. So this was the very first biological sample that went through to the Cryo SEM, and this proved that the whole system worked. So we ended up with a pathway where we can take now our samples through cryoclem, through freeze fracture and etching. We've attached this little cryotransfer system to the cryo ultramicrotome, so we can take block faces of cryo-sectioned samples and take them through to the cryo SEM. And as you've seen, we can also do cryo ion beam milling and take those through. So many different biological methodologies. So that's the work that we've been doing over the past years, and culminating this year in these new pathways. But what are we working on now? This is always the interesting component to see where do we actually go from here. We've mentioned light stimulation, but of course another component is electrical stimulation. There are many physiologists in the world who like to stimulate cells and look at them in under electrical stimulation conditions. So we've been working on taking the light stimulation module and exchanging it for an electrical stimulation module. So this will be where the sample would sit inside here on maybe a cell culture on a sapphire disk, for example. And we've modified one of the components of the high pressure freezer to become a little capacitor which will store electrical energy to stimulate the sample. So we can place the sample inside the chamber, and we can check that our power supply is ready on this middle plate by pressing this button, and then you can give a stimulus to the sample, and then you can freeze it, and you can adjust the timing of the stimulus to freezing according to your needs. So this is something that we've been working on, and we will launch this in September this year. But to get back to the real story, so these were just the tests that we did to show the difference between the electrical stimulation and non. But to get back to the real story, what about developments in protein crystallography? Where can high pressure freezing help us here? Earlier in the year, I was in a couple of synchrotrons around the world, one in Japan and one in Australia. And of course, protein crystallography is utilizing synchrotrons heavily for their beautiful X-ray beams. And we were talking to many customers about how do they prepare their samples. You alluded to the idea of lifting protein crystals with a loop out of a liquor earlier on. Well, the problem is often trying to freeze that protein crystal before you image it by X-rays. The problem being that the liquor that you grew the sample in is not good enough to freeze the sample correctly. It causes all sorts of problems, and you don't get a good cryoprotectant effect. You've got to keep hunting for a cryoprotectant, and this can take many, many months. So what we've done is This is the normal pathway where you'd find your protein, you'd then screen it for a suitable cryoprotectant, which takes a long time, before going into the X-ray beam, of course, to discover the crystalline structure of your new protein, which of course leads on to drug discovery. So what we've done, we've taken our high-pressure freezer and developed it to fit the loop and the protein crystal. And we're working on this now to allow the protein to be simply lifted out of its native liquor that it was grown in and taken to the high-pressure freezer. And we think that this will be quite a big breakthrough to help save many, many days, weeks, months of time in helping develop this part of the process. So we're working on this now, and we should be finished in another year. So this time next year, we should be ready with a system that can actually do this. So there is the future of high-pressure freezing for protein crystallography. So I hope that's interesting information for you. And all I have to say is thank you very much for listening. Thank you.
Yeah. Thank you, Ian, for a very nice talk.
Pleasure.
This is one. Hello.
Thank you for a very nice talk. I have some questions regarding the cryoclam. So what's the typical size of the sample that that can be put on this? And what is the resolution that we generally achieve using this microscope?
The size of the sample is
the thickness, I mean.
Sorry?
The thickness of the sample.
Oh, the thickness. This would be the thickness according to how you prepare a sample for plunge freezing.
Okay.
So you can use the Vitrobot or the grid plunger to blot your sample. You produce a very, very thin layer on the grid bars of the grid and plunge freeze. So very, very thin. Usual standard technique.
Okay,
to get
and
the
what's
ice.
the resolution that we get with the light microscope mainly?
Good question. It's got a 0.9 numerical aperture lens. You can get down to a working distance of 0.25 microns. The resolution, I cannot remember. Sorry, I can find out for you.
And one more question. So, if we have a cellular section for the clam, is it possible to do a confocal imaging before going for the EM?
We're working on that now.
Okay, good, thank you.
Very good question. Yes, we're taking the idea from the standard fluorescence microscope to the confocal. We can't see any problems. Everything fits. We've done the initial tests. It does work. So fingers crossed.
Hopefully. Thank
yes.
you.
I'm having one question, sir. You discussed about cryo-saw.
Yes.
So how you are managing the heat which is generated during the cutting of that?
What I omitted to tell you was the cryo saw is actually sitting in liquid nitrogen. So this is a liquid nitrogen cooled system. The saw itself sits halfway into the liquid nitrogen. And we have the motor drive external to that. And the friction involved in the cutting process is the heat produced is drawn away through the metal surrounding the sample in the carrier, so we don't get any melting of the sample. So it all remains cold. We were also worried about that, but it didn't happen.
Okay, thank you.
Sorry. Thank you for that introduction. I have just one short question. As you introduced the clam system that
yes.
can be make your grid visible before you put it into the microscope. And I have one question about since when we reload the sample, when you check the sample on the cryo box, some cryo environment, after that we need to transfer the grid to a cryo team holder, for
yes.
example.
Yes.
During this period, I think the grid we made rotated out. How do we find the grid at the box we marked before?
Yeah, software.
Software.
Yeah, prior to removal of the grid from the light microscope,
yeah.
we have some points of interest which we can find literally, and we locate those regions, and those we use for orientation.
But then we need a special grid with markers? For example, ABCD, or we can use standard like quantifield.
You can use a standard grid. If you use an ABC grid, that's also fine. But
I was thinking they look maybe like identical for all the
yeah, they do,
squares.
but you can find regions of interest and areas which are slightly different, which you can mark
Okay,
inside.
so we still need some help with if we have some slightly different on the details of special copper nice holes.
You can, yes, yeah, you can do this. But if you've got a special grids, then this is also helpful if you want to have a little bit of help in
So do
orientation.
you think it's possible to load the sample first on TM grid, TM holder, and then check inside this clamp system?
That will probably be the next step.
Oh, okay.
So at the moment we have a universal system.
Yeah, the working distance, everything. Yeah.
If we do it this way, then we have to accommodate every single type of cryo TEM holder inside, and this bit is
or maybe
rather
we can
difficult.
produce a standard holder for different microscope also from Leica. I'm sorry. So thank you for the comment.
Nice idea.
Yeah, thank you for that.
So you have the cryo clamp system, and whatever is it, it seems like there is still a time lag between your light microscope and the time that you freeze. So is there any way to minimize, and what is the minimum time lag between the image in the light microscope and the time that you freeze?
This is a few minutes. So after freezing the sample, it depends on the process you use, but the little transfer device that we have, we can link that to the grid plunger, for example. So if you've plunged frozen your single particles, you can then load the grid directly into the transfer system and then load it into a cartridge. So this takes maybe 2 minutes. And then to the microscope. So you've got, I would say, a timeline of maybe 3 minutes, 3 or 4 minutes. Somewhere on there.
Hi, Ian. Thanks for the very nice presentation. Leica always fascinates me with this small techniques and everything. So I did my PhD from Vienna, from Max Perut's laboratories. So I remember that 2014 September you have this prototype of cryo clamp. Is it already in the market? Is it commercially available?
Yes, it is. Yeah. So
Okay.
the system you saw is now. This was developed in EMBL in Heidelberg with John Briggs' team, and this is now available. Yes.
Okay. So a technical question. Can you hear me? So a technical question is that while transferring, the percentage of contaminants can increase, right? And when you transfer it, so I mean, how you can minimize that, or I mean, what kind of percentage you have seen that it's like?
Yeah, it's a good question because I opened up with showing this nasty thing called ice, and this nasty stuff called ice always hits us. And there's one thing which you can do, which is so simple, and that is speed up your movements. I know it sounds crazy, but it really, really is true. We did some tests only last week on the system because a customer was saying, I've got this ice forming, and we were scratching our heads wondering why. When we did this maneuver, you have to remove the transfer station from the microscope, the light microscope, to the EM, and they were pulling it out very, very slowly. And unfortunately, that caused a 100 centigrade rise in temperature. When we do it, we sort of do this, and thank you very much, job done. So it was simply the speed. So these are the minor details, it's the hints and tips that you need to know around a system, which really do help to give you the difference between a good result and the poor result.
I just need a internal information. So I mean, IMBA, Tom and Gunter Resch, they were working to get the prototype of this. Do they have it already?
In where, sorry?
In IMBA, this EM facility, Gunter Resch and Thomas?
Yes, we put that in last week.
Do they have it now?
Yes,
right?
they do. Yes,
okay,
yes.
Perfect.
Yeah.
Thanks a lot.
Yeah, okay, thank you. IMBA is in Vienna, so this is just down the street from where we work, so it's nice to have a close relationship to talk to people.
Good? Good, okay. If there are no more questions, let's thank Ian for a very nice talk.
Thank you very much.
Thank you, Ian.
Thank you.
This is a small memento for you.
Ooh, thank
Yes,
you
sir.
very much. May I help?
It's again the same.
Wow,
It's,
fantastic. Thank you.
local
Nice. Thank you.
artisans